and welcome to Audi TV, the podcast. Aircrafts are supposed to fly. Cars, preferably not, although some of them would be fast enough. Aerodynamics is the magic word for lift, or its opposite, downforce. But what's behind it all? Audi TV took a close look at large jets and small cars to find out how they achieve the desired effect.
Air. You can't see it, feel it, or taste it. Air seems to be nothing. A medium-sized passenger jet, with full fuel tanks, laden with luggage and freight, with crew and all the seats occupied, this colossus can weigh up to 250 tons. And you wonder, how can it possibly float in the air? The answer, air is certainly not nothing. At the Munich University of Technology in Garching, a whole department is devoted to the study of air, or rather, aerodynamics. Here in the wind tunnel, Dr. Christian Breitsamter, head of the Aerodynamics department at the Munich Technical University in Garching, and his students are looking into the conditions that keep those massive aircraft aloft. What looks a bit like an oversized spearhead is in fact a model wing. Its cross-section is typical of most kinds of aircraft wing, so it's good for observing aerodynamic effects.
The classic wing section is shaped like a tear or droplet, with a sharp trailing edge. This sharp edge has an important effect on the lift generated at subsonic speeds. The lift comes about because the pressure on the upper surface of the wing is lower than ambient, and on the underside, it's higher. That's to say, the pressure difference between the upper and lower surfaces produces an upward force. That's the lift that balances out the weight of the aircraft.
A typical wing is more or less flat underneath, whereas the upper surface is curved. So, while the air passing under the wing can take a direct path, the air above it has a longer route to travel. That means the air moves faster above the wing, and the result is reduced pressure compared to the underside. The airflow sucks the wing upwards. And it's not just the shape of the wing that's important for the aerodynamics.
For transporting payloads, either passengers or freight, an aircraft has a tubular fuselage with a more or less circular cross-section, like an elongated droplet. This shape minimizes the drag, that is, the air resistance, but maximizes the volume for holding the payload.
Cars are not expected to fly like aircraft. On the contrary, while the shape of an aircraft is designed for lift, with a car we want to reduce the lift as much as possible. Cars are not supposed to take off, but to stay firmly and safely on the road. The Audi wind tunnel at Ingolstadt is one of the most modern in the world. For years, the subject of aerodynamics has played an important role. The rotor has a diameter of 16 feet, and the motor consumes 2.6 megawatts. It can produce wind speeds of 185 miles per hour. The vanes make sure the corners create no turbulence. The wind tunnel provides almost unlimited options for reproducing realistic driving conditions.
Im Automobilbau wird
When you build a car, the basic form inevitably produces lift, which is undesirable when driving on the road. The lift in a normal car comes about because the air flowing over the top of the car has to cover a longer distance. And so there's an upward force working against gravity. That's why we optimize the outer skin of a car and also the underside to produce less lift.
That a body shape like this leads to optimum aerodynamics and a low CD value appears to be quite plausible, but that the underside also plays a significant part. Not many years ago, engine, gearbox, propeller shaft and other parts on the underside of a car were largely exposed, so the air couldn't take the most direct path underneath. The result was turbulence and generally poor aerodynamics. That's why modern cars like the Audi A4 have what we call an aero floor pan, cladding elements on the underside that produce as smooth a surface as possible. And a lower drag coefficient, or CD value, besides many other positive effects, also means lower fuel consumption and a higher top speed. The car designers have taken a leaf out of the aircraft engineer's book, particularly in motor racing. Modern racing cars have one important thing in common with aircraft: wings.
The basic difference in the aerodynamics is that aircraft have to be efficient flyers. That's to say, when an aircraft takes off, the wings produce lift and get it airborne. With a racing car, it's just the opposite. The wings are mounted upside down and generate a downforce. They press the car onto the track. So we can corner at much higher speeds than with a normal car. It's a bit like an aircraft with the flaps extended during the takeoff and landing phases. The air that flows under our wings has to cover a longer distance than the air flowing over the top. Fast-moving air produces a drop in pressure on the underside of the wing, whereas there's increased pressure on the top, and that pressure difference presses the car onto the road. With the various elements that produce downforce, such as aerofoils, front diffusers and the floor pan, we generate so much force that above 135 miles per hour, you could drive on the ceiling.
But in spite of the many aerodynamic features that cars and aircraft have in common, there's one important difference.
You have to distinguish between visual design and aerodynamics as a condition for determining shape. With an aircraft, of course, aerodynamics are the main criterion. Visual design per se plays no part, because the sole purpose of an aircraft is to transport things. With the new Audi A4, we've managed to marry aerodynamics with design. The new Audi A4 has a CD value of only 0.27, well ahead of its competitors.
Cars and aircraft. Two different worlds. Aerodynamics is where they intersect. After that, they go their own ways. Let's be thankful that they do.
Thanks for joining us here at Audi TV, the podcast. Until next time, bye-bye.